basic concepts of probability. Probability is the likelihood that a certain event will occur. However, in the discussion of probability, we need to differentiate between theoretical probability and empirical, or we also call it experimental probability. For example, when you flip a coin, you have 50% chance of coin landing heads up and a 50% chance of coin landing tails. Suppose I flip a coin 2 times. What is the theoretical likelihood that it will land heads up only one of those times? So I could get head first and then tail, and I could get tail first and head. Right? I also could get just tail and heads and heads. So out of 4 possible entire outcomes, there are 2 of them where contains exactly one heads. Therefore, there is 50% chance that it will land only one head. Does this mean that every time you flip a coin 2 times, it will land heads up only one of those times? No. As I wrote it here, no, it could also result in tail and tail or head and head. So it's important to differentiate between theoretical and experimental probability or empirical probability. So theoretical probability that an event E, so this is a notation we use E, or sometimes we use capital A, capital B, oftentimes capital letter to denote an event. In this case, the previous example, flipping coin, event will be landing on a heads up. So probability of this capital P means probability of event E is number of favorable outcomes divided by total number of outcomes. So this notation is referring to probability that E occurs. Let's look at an example. Using the formula above, we're talking about this formula, number of favorable outcomes divided by total number of outcomes. Using the formula above, determine that if a single coin is tossed 3 times, find the probability that it will land tails up only 1 time. So before we calculate this probability, we need to find out total number of outcomes. So how do you find the total number of outcomes? So let's list them. So let me organize it this way. So for the first coin toss, it will be either head or tails. And so we have first 2 cases, 2 possible outcomes for the first coin toss. Let's say I get heads up first. Then for second, I can get another head, or I can get tail. Then for third one, for this one also, I can get another heads up, or I can get tails for the third. And this one also has heads and tail. So what this is saying that I could get heads up, heads up, heads up, or heads up, and tails, heads, tail, heads, heads, tail, tail. So we're listing all the possible outcomes. So let's say the first one was tail. Similarly, then I can get heads again for the second. Well, not again, I guess, because it's different, and tail, and heads and tail, heads and tail. So let's count how many total possible outcomes are there. There's 1 outcome here, 1, all heads, 2, heads, heads, tail. So we count all of these. 3, 4. And similarly 1, 2, 3, 4. So there are total 8 possible outcomes. So in order to solve this problem, probability of event E, let's write tails up only one time. We can also just label this event as a E. So let's label this as E. So probability of E then is out of total 8. That's a total possible outcome. There are total 8 possible outcomes if I toss the coin 3 times. And out of these, which of these have only tails 1 time? So we just find them. Tail only 1 time. So this one right here, let me use different color. You can follow this. This one right here, head has tail, only has 1 tail. Has tail has also has 1 tail, so we have 2. And lastly, tail has also have only 1 tail. So 3 out of 8. And the favorable outcome is in this case is exactly 1 tail. So probability of this is 3 over 8, which is 0.375. That's the probability that if I toss a single coin 3 times, it will land tails up only 1 time. Another example. Using previous formula, determine if a coin tossed 2 times, in this case not 3 times, find the probability that it will land at least, we have to pay attention to this wording right, at least once. So let's list all the outcomes. So if I get heads first, I could get heads again or tail. If I get tail first, I can get heads second and tail again. So total 4 outcomes. Okay. So out of total, so probability of an event, let's call it A in this case, at least once. Let's call it this event A. Probability of A is total out of 4. Out of 4, how many are there? We count the number of favorable. In this case, at least once means 1 tail is okay, or 2 tails. So if to count the one with at least 1, which means 1 tail or 2 tails. So heads, we don't count that one. Heads, tail, that's okay. Tail, heads, that's okay. And tail, that's okay. So 3, we count total 3. So 3 out of 4, which is 0.75. So there is 75% probability that when I toss a single coin twice, they will land tails up at least once. Let's look at this example. Kathy is interested in the likelihood of having exactly 2 daughters. Assuming that the boy and the girl babies are equally likely, find her probability of having exactly 2 daughters in the following cases. So let's say she has a total of 2 children, or wants 2 children. So again, we list all the possible outcomes. The reason we're listing it, because we need to know how many are there. So we just count them. So we could use that like this style, like a tree style of counting it. We can also list them. But when we just list them, make sure you count all of them. So this is what I mean. We can say, okay, she could have a boy and a boy, boy and a girl, girl and a boy, and girl and a girl. So order matters. So boy and girl and boy, we have to count separately. So there are total possibly 4 outcomes. And we could also have done this, just like the coin. First, second, boy first, then we get boy and girl. Girl first, then we can also get boy and girl. Still there are total 4. So out of 4, only, one outcome is the 2 daughters, 2 girls. Therefore, 1 out of 4, 0.25 is the probability. But what happens she wants 3 children? Again, we have to list all the outcomes. So let me count it. It could be all boys. It could be girl, boy, and boy. It could be boy, girl, and boy. Boy, boy, girl. Boy, girl, girl. just write all of them. And girl, girl, and boy, and all 3 girls. So let's say she wants to have all two daughters, right? So 2 girls. So out of all these, there are total 8 outcomes. What are 2 daughters? So let's see. 2 girls. So this one. Oh, I did it again. I meant to use a highlighter. This one, and this one. Exactly 2 girls. So we don't count this one in this case. If you said at least 2 girls, then we would include this one. But the problem said 2 girls. Exactly 2 daughters. Therefore, it's 3 out of 8 is the probability. So let's look at some more basic definitions. Property of probability. An event, as we just looked at some examples, such as having 2 daughters, exactly 2 daughters, or flipping a coin and getting at least 1 tails. Those are called event. Probably they're a set of outcomes in an experiment. So this is what we as a human decide to find the probability of such a certain event. Flipping a tails out of 50 coin toss, for example, is an event. Sample space for an experiment is a collection of all possible outcomes and results, which we also saw, right? We list all the possible combination of boy and girls, the previous example. That's an example of sample space. So recall the probability of event is number of favorable outcome divided by total number of outcomes, possible outcomes. So let's look at more example. Now in this case, we're rolling a die. Consider a regular 6-sided die, and regular die has sides labeled 1, 2, 3, 4, 5, and 6. Determine the probability of following rolls. And we're here assuming that the die is not loaded. Loaded die means it's way different inside of the die, so certain number has more chance of getting rolled than others. But in this case, regular 6-sided die means it's equally distributed the way it is. Okay. So we're going to roll once, right? So in this case, this will be the sample space. Sample space is the total 6 of them. Right, so keep that in mind. So number 2, there's only 1 of them, right, out of total 6. So 1 out of 6 is the probability of getting 2. How about 8 is being rolled? But there's no 8 in the sample space. It's not possible outcome. Therefore, it's 0 out of 6, which is 0. 0 means there's no chance, there's no probability it will happen. Number other than 2 is rolled. Number other than 2 are 1, 2, 3. Oops, I said other than 2 in row 3. 1, 3, 4, 5, and 6. There are 5 numbers. So 5 out of 6. And another way we think about this 5 out of 6, other than 2, we can also just think as 1 is the 100% minus 1 out of 6. So number 2 being rolled is 1 over 6. So I can just subtract it from 1. Then we also get 5 out of 6. Number less than 7 rolled. But all numbers are less than 7 in this case, right? 1, 2, 3, 4, 6. 1, 2, 3, 4, 5, 6. All those numbers are less than 6. So 6 out of 6, which is 1. That means it will certainly happen. So let's look at more properties of probability. As we said, E is an event with a sample space. Let's call it S. That is, E is a subset of S. Then the following property holds. The probability of an event is always between 0 and 1, including 0 and 1. So 0 means it's an impossible event. 1 means certain event. Okay. And here, if you want to use percentage, we multiply 100 to the probability value. But usually the value itself is a decimal or a fraction between 0 and 1. So again, if in probability of impossible event, we get exactly 0. Probability of certain event is 1. Certain event is an event that would definitely occur. Okay, so we need to be careful with the language here also, the impossible means as it's just not possible. Having 0.00001 is not impossible. It is still possible. There's a difference between possibility and probability. Okay. Experimental probability, also we call it empirical probability, is essentially calculating a probability from experiment. So an important aspect of conducting experiment is recording result, then analyzing result. However, in experiments, results often do not match the theoretical expectations. So let's look at an example. Suppose I flip a coin 4 times, and how often would you expect, okay, focus on this word expect, to see heads, and how often would you expect to see tails? Reason based on the theoretical understanding that you have 50% chance to get heads or tail. Okay, so imagine we actually flip a coin. So actually, I would like you to actually flip a coin. Get a quarter, penny, whichever coin we have. Flip it 4 times. So I just flipped it myself, and I got actually tail, heads, heads, and heads. And you might have got 2 tails, 2 heads, but not all of us would have gotten exactly 50% chance of getting heads or tail in this experiment when I clip 4 times. Okay, again, some of you guys might have gotten tail, tail, heads, heads. Again, it depends, right? And that's the whole point of this experimental probability. What we see in this example is that sometimes experimenters do not match theoretical understanding of events. Particularly, this is the key point here, if we do only few experiments. However, if we instead flip the coin 1,000 times and record a result, we will see our probability more closely approach expected outcome of 50% heads, 50% tails. And this is called the idea of law of large numbers. So the more and more experiment we run, the experimental probability will get closer and closer to theoretical probability. So that's called the law of large numbers. As an experiment is repeated more and more times, the proportion of the outcome favorable to any particular event will tend to come closer and closer to theoretical probability event. This is known as the large numbers. So here we did 4 times, but if we do actually 100 or 300 and 1,000, 10,000 times, it will get closer and closer to 50% between tails and heads. And that's also the same for the dice. If we roll a die 1,000 times, then those 6 numbers should have equally likely chance of getting selected. Complete closer to theoretical probability of 1 over 6. You might not get exactly a 1 over 6 if you only roll 50 times, but again, as we do more and more, we get closer to theoretical probability. And let me point out one last thing, is that both theoretical and empirical or experimental probability, the way we calculate is same. It's similar formula, right? Well, exact same formula. It's just that we have to differentiate where you get this number from, right? So the bottom is always total number of outcomes, total number of outcomes. So for example, in a die, there's total 6 number of outcomes if you roll only once. And in the numerator on the top is number of ways of the event, the event that we're interested in. Number of events. Well, let me write the event. Event can occur. So the event is something the problem usually defines. Just like, getting 2 daughters only, or tail, at least 1 tail, things like that.